So welcome to lecture 6 of MCS 471. So today we will consider the root finding problem again, but now without using derivatives. So last lecture we considered Newton's method. Newton's method is in many cases actually the gold standard for root finding because of its quadratic convergence, which is really fast. But one troubling issue is that it requires the computation of derivatives. So last lecture we used symbolic computing to get the derivatives, but actually this might still have been somewhat of a concern. So today we will see that we can also compute roots quite fast at a very good convergence without actually computing derivatives. And that method is the secant method. We will define the methods, and defining means that we have a good working Julia function. And we will prove that its convergence is superlinear. Superlinear is in between a linear and quadratic. So it's not quadratic, it's not linear either, but it is close to being quadratic. We will see that for many practical purposes, the convergence is actually indistinguishable from quadratic convergence. Remembering that quadratic convergence only happens in the limit when you are already sufficiently close. So in the first part of this lecture, we will look into the secant method. In the second part, we will actually go back to bisection. Why is that? Because the secant method also has a vulnerability. And we will expose a bad case for which the secant method utterly fails. But we can fix this, and this is called the method of false position. And this will combine the secant method with the bisection method. The bisection method, as you may recall from last week, was a very simple method and gave us 1 bit per step at the cost of 1 function evaluation. Bisection is actually quite robust, but converges rather slowly. So that was the motivation to go into Newton's method. In overall, we will have now seen 3 different methods, or actually 4. The method of the false position is actually our 4th method. But many good programs actually will not rely on any single idea, but will be a combination of many ideas. So we will shortly close this chapter on root finding. But we will return to this later in the course, but know that many good programs, or any good program, will have to combine ideas. All right, then what is the secant method? A picture explains it. We have 2 points A and B, and we connect them. So the secant method is very similar to the Newton's method, is that we reduce the root finding problem to the root finding of a line, and that is easy. So we have the blue curve, the red line, and the next approximation to the root is where the red line intersects the horizontal axis. Now, for the purpose of this picture, this secant connects 2 points that are very far away, but you could see that the slope of the red line is trending upwards. So it has the same upward going trend, going from A to B, the same slope, if you like, as the blue curve. So the secant is often seen as an approximation for the derivative. So you can see this approximation also here. So remember rise over run for the derivative. So we have the two endpoints, A and B, and we construct what is called the secant line. In the limit, if A is very close to B, then the secant line is indistinguishable from the tangent line. And that's also actually will be the intuitive, the geometric intuition for which the secant method can converge just as fast as the Newton's method. All right, so that's the idea. And we also have an equation. We don't yet have a formula. Let's derive a formula. So that will give us essentially the essence of the method. So we are having the secant line, and we compute our next approximation. So the next approximation here, we will call it C. So we have A, B, and C. And we compute the next approximation where the secant line meets the horizontal axis y equals 0. So we solve for C, and then we have an explicit formula for the method. So that's the formula, and actually it's a very good formula because you could see this A, B, C as a sequence of points, and what is here is what we called before the delta x. It's the correction term with Newton's method, and that's good. So the format in which this formula is written is very convenient to get an estimate. So we subtract or we correct something from B to obtain the next approximation C. So what we use as the correction term in a converging method will be an estimation for the forward error, which I here now denote with delta x, or delta r if we use r for the root. All right, so here it is again. So it's an iterative method. So this is another way of seeing this. So we've seen the fixed point iterations, and now actually this iteration is a two-point iteration. So what I'm drawing here is that we see this formula as a G, where we use the previous 2 points to get the next point. So in a way, this new method, the secant method, fits the pattern of fixed point iterations. So it is within the same family, but now actually we use not only the previous points, but the previous 2 points. And since we are now going to the x's notation, so the delta x is actually now more natural to use. And you see that this correction term is actually used first. All right. This is the pseudocode already with the 2 stop criteria. So actually there are 3 stop criteria. So we want to bound on the amount of work. So we have the capital N on the number of steps. Then we have the bound on the forward error and the bound on the backward error. And in this pseudocode here, we actually are doing 2 function evaluations per step. But if you think about efficiency, the cost will actually also be 1 extra function evaluation per step, because we could store the function evaluations at the 2 previous points. So actually we do 1 new function evaluation then at the next point. So notice that there is no x3 here. So the benefit of pseudocode is also you see that the x3 here actually we replace the 2 points, the current 2 points, by the next 2 points. Notice that the order of assignments matters here. So we first need to assign to x1 before we update x2. So this pseudocode still has benefits. So I was earlier at some point rather saying too enthusiastically that with a clear programming language, the need of pseudocode is actually not really necessary. Well, pseudocode you could see as the intermediary between a formula, so here the formula on top of this slide, and the transition into a real algorithm. So in a way, the pseudocode is almost sufficient to get to the actual algorithm that we code up in Julia. But it's still not there. All right, so here we arrived then at our Julia function. So we have a function in one variable on input, and we now have 2 starting points. So these are the 3 arguments that any user must supply to this function. So these are the 3 mandatory arguments. Then we have our default arguments, which are tolerances on the forward error, on the estimated forward error, and the tolerance on the backward error, also called, the backward error is also called the residual. So I called them fx, because this is f at the function value, and dx for the tolerance on the delta x. They're both set to 10 to the power minus 8, and we allow now 10 iterations, a little bit compared to Newton's method where we allowed 6, because we know that we expect quadratic convergence. Here actually we allow 10 iterations. In actual situations, I should have pointed this out also with Newton's method. In actual situations, you allow for Newton's method only a couple. Actually, 6 was a little bit too generous in our previous lecture. Keep that in mind once you go to actual applications. So Julia has the main benefit that you write your documentation strings before you get to the actual prototype. This has the benefit that for every argument, you actually think what its meaning is, if you do it properly. All right, it's good to have an example. So the example, we will actually might have been the example that was on display. We actually are computing pi over 2, which is the error of the cosine. So the cosine, a nice continuous function that we can all evaluate. And we have our 2 points. We will return, of course, an estimate for the root. And if all goes well, and with this example, everything will go well. If all goes well, that's also what we need to return. But iterative methods may fail. And then in case when they fail, you still want to have some indication on the quality. So we have a tolerance of 10 to the power minus 8, but it can be that we only get 10 to the power minus 4. So not all our efforts will be in vain, even if the tolerances are not being met. All right. Good. The definition of the function is actually quite straightforward. So here you see that I have stored the function evaluations. So we have one new function evaluation in every step. So the fx2 is actually already the function evaluation at the new point. So one new function evaluation in every step. So that's actually the point also for going to an actual algorithm, an algorithm that can be executed by a computer. Notice selling point, no derivative here. So in a way, this can go twice as fast as Newton's method. As we'll see later in the course, computing roots, the function evaluation can actually be the most dominant computation. So we also do some subtraction and a multiplication, but compared to the function evaluation, this could actually be in many applications, that is actually the most dominant cost here. All right, then the other important part is the stop criterion. So there is already the stop criterion in the for loop, so we will never go on to infinity. So we check the stop criterion, and then there's also the printing. So we print what we are interested in, the value of the root to its fullest precision for in scientific notation. So it could be if we are computing 0, that the fraction has no meaning. But the exponent, and then we look at the exponent. But in any case, we look at the exponent when we consider what we use in the stop criterion for the accuracy. All right. So we often, in the previous lectures, we ran it as one program at the command prompt. There is a hybrid here that I want to point out. One can store functions in separate files. I have strongly recommended, when you use the Jupyter notebook, one cell per function. You could also have the rule that every function has its own file. And this is very useful. I mean, in this class, we actually won't do large programs. So in that sense, this is a little bit out of the scope here. But I just want to point out that in a Julia session, you can include Julia code. And in a way, if you are constructing your Jupyter notebooks more in a modular fashion, which we will not do, our Jupyter notebooks have to be self-contained. But if you would go to larger projects, you don't want duplication of the same code, which leads to version issues. So you can include in a Julia session the function definition. The include will actually also do the compilation for you. And then you can run the secant method and eventually rerun it. So here, this is with the default parameters. And of course, the main point here is that consider the almost perfect evolution of the exponents here. So 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 8. So in the quality, in the accuracy, we see that the correction term in order actually always decreases with one full order. And you can also see this here, the correction term. You can see this by comparing. So we are correcting 10 to the power minus 4. With the function evaluation, we actually are evaluating the function at the current root. So you see that there is kind of off sync. So you could say that, hey, the backward error is actually so much more accurate than the forward error. So this should be kind of, if you see ever that, this could be that you get a very sharp function or a very flat function. But no, this is mainly because this error here is actually the error of the more accurate solution. So in the printing of the roots, we are lagging one step behind compared to the printing of the forward, of the residual. All right, great method. One function evaluation per step and quadratic convergence. Two exercises which are very similar to the two first exercises in the last lecture. Experiment with what happens when you pick the points closer. So we started here at 0.5 as the first value for this root, and then you can take the second point, either extremely close, and we actually remember that the root of this nice cubic was 0.6 something. So what if you take 0.6 for x2? For which choice does the secant method actually work best? So you might say the first one, because then the secant line is almost indistinguishable from the tangent line. And you actually do run Newton's method. But perhaps 0.6 is better because it lies closer to the root. So roots can have complex conjugated. So the roots can be complex conjugated, but if you are not computing with complex arithmetic, you won't find them. You can kind of trick it. So you can adjust the code so that your initial points are actually have non-zero imaginary parts. You may have to adjust also the prototypes of the function. So these are now forced to be float 64. Remove that. And perhaps you may have to change other things, but the complex arithmetic works in Julia. All right, this corrected. Now we observed quadratic convergence, but you may want to say, you know what, the example was simply so nice. So this is in some sense also a mathematical course. Let us prove the superlinear convergence. Now I will go rather fast through these statements. No, I will not go fast through the statements. So that I will spend most of the time on the statements of the theorem and the lemma. The proofs themselves, I will go over faster, mainly pointing at the ingredients. So why is this so nice? The superlinear convergence. It involves actually the golden ratio, which was known in antiquity. The ancient Greeks knew the golden ratio already when they built their temples. And we will see actually the golden ratio again on Monday, next lecture. So the golden ratio is kind of a very nice constant that comes up there. And we will actually derive the golden ratio as a solution of a quadratic equation. So the 1.6 is close to the 2. Remember how we defined quadratic convergence? The ratio of two consecutive errors is actually quadratic. So the next error is the square of the previous error. So that's the other way of actually correctly saying it. Here we get something very close. So the 1.6 is not close to 2 by no means, but in practice it actually is. For convergence, we actually don't see the difference. All right, so it's important to know that also the secant method will not work very well at multiple roots. We saw that with multiple roots, the derivative is 0, and then we divide by 0. So you could also say, hey, this method is very good for multiple roots. Well, it isn't, because that is also a precondition for this convergence. So the secant method will not help us with multiple roots. So that's also the important thing. And actually the first important thing is that this only works for converging methods. So it's expressed here in words, but that's also actually the first condition. So we will see that things can go badly wrong with the secant method. But if it goes well, it is quadratic convergence. All right. We have now three technical lemmas, and the lemmas are important because they present us with more and more accurate relationship between the errors. So what is important in the lemmas is that you kind of see how you can get to the proof of an important theorem like this. The proofs themselves are actually important because of Taylor. So we derived Newton's method via the Taylor expansion. Taylor occurs here again. So Taylor will almost make his appearance in every week. So this is another importance of Taylor series that come up here. Now, what this actually also indicates that under the assumptions of the theorem, so the derivative at the root better not be 0. So you see that there is the constant factor here that comes in. So in a way, seeing the statements of the lemmas is actually also important to know a little bit more about what the theorem is. So in the theorem, we were focusing on the golden ratio. Here actually there was also a constant c in there. In this course we actually also care about constants, not so much about the orders as well. And you can see that also here that the first derivative will actually be a spoiler. So the method will also not work very well when the derivative gets very small. So and that is not the fault of the secant method. That is a problem, that's a difficulty with the problem. So the flatter the functions at the root, the harder. And actually you also see the curvature playing a role. So the second derivative actually comes up as well. And actually that might actually be helpful sometimes. All right. So how does the proof work? Well, we are interested in the expressions of the errors. We use the definition of the secant method, and we do some manipulations to get the previous errors in there. So we are subtracting already here in the definition of the error, the root, and then we use the fixed point notations to manipulate this. And then we apply the Taylor expansions to further simplify. So higher order terms we typically them. So this is also important in the analysis. Now I'm restricted now with the slides, so you see that I have labeled the equation on the previous slide as 1, and now I have the next equation labeled at the bottom here as 2. So on a nice whiteboard or blackboard you will see them next to each other. I can't really show these next to each other, but I actually use these two equations, these two expressions, as actually the derivation of a next expression. So you can kind of see that the error in the k+1 step is depending on the error of the kth step and also the error on the k-1 step. So in a way, intuitively, that we have the error in the next step depending on the error in the two previous steps is actually also mirroring the fact that the secant method is a fixed point iteration formula that uses the two previous points. Here actually we are using the two previous errors, which is also kind of nice. I mean, the algebra of the proof is technical, but you can kind of see intuitively why it is true. All right, then we get very close to the statement of the lemma. So actually I should also have indicated why you use Taylor. Well, we have the derivatives coming in very naturally. So the derivatives, and note that we only truncated after the second order, because that actually allows us to have the second derivative also in there. So with some algebra, we then find actually a relation, and this is actually very close to the main result already. So this has all the main actors in it. At the right-hand side, we have the two errors of the two previous steps, and we have the first derivative and the second derivative at the root. So everything what we are saying holds asymptotically. We are not at the root, but it is actually the behavior of the function at the root that is going to determine everything. All right, so we have one more simplification to go. And in a way, I'm using this as just a restatement of the first technical lemma. QE. All right, I have to speed up a little bit. Although the proofs of the lemmas actually now get shorter. And the second lemma actually will give rise to the quadratic in the golden ratio. So actually, not to put some much suspense in this, but we will find the golden ratio. So here in the lemma says that there is an existence of a constant. So there are constants there. So the nice thing about any method that you want is that they are predictable. So if everything goes well, everything is actually quite boring. So it's very predictable. So there are constants in there, but they don't depend on the actual step anymore. So you see what this lemma does, it rewrites. So the C involves the main properties of the function, the first two derivatives, but you can rephrase it that the constant C actually gives rise to two new constants, K, the capital K, and the R. All right, I will not go through the proof here, which is a rewriting of essentially assuming that there is something, assuming that there is a convergence rate, assuming that there is a convergence rate R, then this R needs to be looking at a very particular way. And that's actually what the proof of the lemma says. So if there is the R, then you have this relationship. The K is actually a simplification of the constants that come up here. Quod erat demonstrandum. So we will get into some more Latin later. Now the point, so the main lemma actually, the proof gets even more shorter. But it's the lemma, the statement of the lemma is for emphasis. So if we have this relationship between the errors, and I now see that there is a typo still after all this time, so this should be a +1. So the ratio with all the consecutive errors will actually give rise to a quadratic equation. So it's even better than the previous lemma. It's not so much that this is predictable, but we also know actually the critical exponent, the R. So we have the value, and we got the value from the solving of a quadratic equation, which gives us the famous golden ratio. All right. We now not only know that it works well, we have done one example, but actually we can prove that it's what we call superlinear convergence. Fine then. So we have still 15 minutes left, so we could leave here. But the method now actually has a bad case. And actually the bad case is already given here by a very nice parabola. So parabolas are very nice functions. I mean, and again, if we have a parabola, we know the quadratic formula. So in a way, you can see that we can read off the roots, and you can see how we can actually see where they are, and you know actually also the parabola. So the roots are -2 and 2. So the picture actually says what the shape of the parabola is. But you see what is wrong. So we start with x1 and x2. And okay, so you could also say that you shouldn't have started in x1 and x2. Fair enough. But so you cannot really force a user to give specific values. So x1 and x2, the red tangent line gives us x3. No problem here, but the next step is the problem. So look at the line that connects x2 with x3. We have a flat secant, which in some sense approximates the tangent line at the top. And in a way, this is also a little bit of vulnerability of Newton's method. So it could be that somewhere, if you are far away from the root, that the derivative becomes 0. So our programs were not that robust yet to detect that. I pointed this out as well. But here also, the algorithm that we gave, the Julia function, was kind of too trusting. So it was assuming that everything would go well. And why would it not be? So it pays off in life to be optimistic. But here the behavior is actually quite catastrophic. Here you see the catastrophe that happens. And that also kind of summarizes up why numerical analysis is so difficult. So you can have a completely correct working function, but what it spits out is actually quite problematic. So in a way, we mentioned not a number, and so Julia doesn't crash on us. So it could actually have gotten a lot worse. So in a way, we are working in an environment where we can divide by 0 and our program will not crash. So we actually see the symbolic infinity. And after working with infinity, we have not a number. So, but not a number is not a number. So and you can kind of see what the parabola was. So one can say, look, well, you kind of use the wrong input, but the wrong input is different from a nil-conditioned problem. So you can actually not prevent the user from giving a nice parabola and two very nice numbers, -1 and 1. So you can't really prevent the user from doing that. All right. Let's now see how we can fix it. And we will get to the method of false position. We will actually combine the secant method with the bisection method. So the bisection method will not fail on this simple parabola. So instead, what we will be doing is that we will keep one of the endpoints. So with the bisection method, we have the bracketing of the roots. So because the sign is different, so we are negative at x1, positive at x2, we know that there will always be a root in between. And our tangent line, instead of replacing by x2 by x, using I mean, if replacing one of the points, we will only replace the point if we can maintain the condition of the bisection method. So the bisection method will keep the bracketing because of the intermediate value theorem and the assumption that the function is continuous. Here we actually keep that invariant as well. And you can see we can kind of combine the best of both worlds, because you can see that the x4 is already quite close. So, and actually, the next step I did not show anymore, but it would almost be exactly at the root. Great. So let's quote this up. So here we have the formula, and the formula is here simply given as the explicit formula that comes from the secant method. So we have a next point, and we can't really work with the delta x anymore. So I was actually the delta x is actually not is no longer that reliable, but we still have an error on an estimate on the forward error, which will be the b minus a, similar to the bisection method. All right. Here we see the hybrid. So we have the c is computed by the secant method, and here you see the moves that we did with the bisection method. And if we store the two previous function values, then actually we can get away with only one extra function evaluation as well. So it's called the method of false position, or in Latin, the regula falsi method. I will go a little bit faster for the definition now. So it is a hybrid. So we have the bracketing. So the regula falsi will only be guaranteed to work if we have the same condition as on bisection. Also, we need to have the same upper bound again on the number of steps, so that remains invariant. So actually here, what gets returned is not only the root, but actually also the bracketing of the root. But we will print out the backward error. So we will actually also print out the function evaluation at the root. So as you can see already a little bit a hint, I have relaxed my tolerances quite a bit, and this is kind of a hint of we can combine the best of both worlds, but actually we won't have the best of both worlds. So the best of both worlds would still be that we can apply this method when we are far away from the root, whatever far away is. So that would mean that we would apply regula falsi for a couple of steps. And actually the couple here is actually 10 again. So again, not quite recommended. But once you are actually with 10 to the power minus 4, you may assume actually that you can apply the secant method directly. So here, these are methods that are still stand on their own. So it is the method of regula falsi is a hybrid, but also short enough to count as one single method. And yes, it may also fail. But let's not get into this. So the font is rather small. That's because it fits entirely on a slide. But the essence is actually given by the code, which resembles very closely the pseudocode. And I did not store the values for f of a, f of b, so they are actually computed. So in some sense, this does 3 function evaluations per step, but this is not an optimized program yet. but it gives the essence. So here you see the running. So on this example here, we actually we have to keep the B. But you see that we are converging, albeit no longer in a superlinear fashion. So the method of the regula falsi on this example here, and it is again the example of the parabola, which converges now to -2 as the root. It converges, but slowly. So it's one method. It's called the method of regula falsi. It's not a hybrid in the sense that if you would know that you have already 4 decimal places, you would actually switch now to Newton's method. And one step of this method will actually give you the correct root. So in a way, the regula falsi is extremely robust, has the same robustness, but actually is still faster than the bisection method. So the bisection method will give you 1 bit per step, or 3 to 4 steps for 1 extra decimal place. So we are actually faster than the bisection method. All right, this leads me then to the last exercise. Consider this function here in the interval -1, 1, and you can kind of read off there is no constant term in this polynomial, so the d root is 0. So in some sense we are actually now computing 0 of a cubic polynomial. And the question is, run the 3 methods. So bisection applies, the secant method applies, and the regula falsi applies. Report for every method the accuracy, number of steps in each run. And I can give you the punchline already. The method of false position will converge quite slowly. Make a plot to explain this. So you can also make plots that actually show the secant lines. And you see that the secant line is actually approaching very, very, very slowly the tangent line. All right, I will stop this.